Good morning, everyone. Let's start. Yeah, so in the previous class, we were discussing the disadvantages of Huffman codes, and that was that if you have a sequence of random variables which you want to compress, then the only way you can get close to the entropy, a constant gap away from the entropy, is by coding blocks of symbols. And but this involves a huge computational complexity, so you want to avoid doing that. So what do we do for compressing sequences of IAD random variables? So towards that, I started discussing about the Shannon-Fano-Elias code. And this is a slightly different approach. Now, we know that every prefix-free code can be represented in the form of a binary tree, right? Where certain vertices of the tree correspond to code words, and prefix-free, the prefix-free property corresponds to the property that no two code word vertices are ancestors, or no code word is an ancestor of any other code word. Right? So that was a technique derived from the tree approach. So we'll use a different approach towards constructing prefix-free codes, and that is essentially by splitting. So instead of viewing code words as vertices on a tree, in this particular technique we'll view code words as points on an interval, or we'll see that the code words correspond to intervals themselves. So right now I'm not said anything properly, so uh, I'll make this statement that I'm making will become clear as I go along. All right, so I introduce some basic concepts. Well, you're all familiar with the notion of the cumulative distribution function for a random variable. Right now, we'll assume that the alphabet is 1, 2, 3 up to m. Okay, so the actual random variable, the actual alphabet may be a sequence of letters. It could be a sequence of ASCII characters. It could be some special characters. Doesn't matter. But you can always map those ASCII characters to a set of integers, and that is going to be important when I discuss the Shannon-Fano-Elias code. So it could be that the actual alphabet is A, B, C, D, E, but then we'll number these, just write these letters in some order, doesn't matter what order it is. So I'll call A 1, 2, 3, 4, 5. So basically, if I have a sequence of letters from A, B, C, D, E, I can replace them with a sequence of numbers with 1, 2, 3, 4, 5. So this mapping is 1 to 1, and we'll assume that this is known. Okay, so we'll fix some mapping of the actual alphabet with the set 1, 2, 3 up to m. Okay, so for our purposes, the alphabet that we have is just the set of m positive integers. Okay, and corresponding to this, we have a probability mass function. So we know the probability of 1 occurring, probability of 2 occurring, and so on, all the way up to probability of m occurring. And corresponding to this, we can draw or compute the cumulative distribution function, which I call f of x. So this is the sum, this is the probability that the random variable x takes capital X, takes any value less than or equal to small x. Right? But in addition, I'll also define this new function, the modified CDF, which looks similar to the CDF, except that I'm removing some component of the last probability. So f bar of x is the summation over all a less than x, px of a plus p of x by 2. All right. And we made the observation that for all symbols in the alphabet, f bar of x is going to be strictly greater than 0 and less than 1. So it's greater than or equal to p of 1 over 2, and it is less than or equal to 1 minus P of M divided by 2. Right, and we'll use this to design, we'll somehow use this to design a compression algorithm, a prefix-free compression algorithm. All right. So before we continue, are there any questions from the previous class? All right. So a key idea that we will use in designing these Shannon-Fano-Elias codes and arithmetic codes, which is sort of for which Shannon-Fano-Elias codes are a precursor to, is the following. So it is so any real number, or in particular any number between 0 and 1, can be represented in its M-array form or K-array form. So take any positive integer k, right? So it could be 2, 3, 4, k. We'll assume that k is strictly larger than 1. You can write any integer let's say n. You can write this as summation, let's say alpha I k to the I equal to 1 to some particular thing, 1 to infinity, let us say. Okay, where many of these alpha i's could be 0, right? So, for example, if you take the integer, say 100, 126, you can so this is the decimal representation. You can write this as 100 plus 20 plus 6, which is 1 into 10 square plus 2 into 10 plus 6 into 10 to the 0. Right? So this should be I equal to 0 to infinity. Basic stuff, not doing anything fancy. So you can write any integer as summation I equal to 0 to infinity, some alpha I 10 to the I. Correct. And this is true for any base system. So here I'm writing it in terms of base 10, but then you can also write the same in base 2, right? So I could also write this as summation, say j equal to 0 to infinity, some beta I 2 to the I. Right? So in base 2 form, each I could write the same integer in base 2. And one thing to note is that these coefficients, the alpha i's, are between 0 and 9. And similarly, if I'm writing it in terms of base 2, then the beta i's, the coefficients, are going to be either 0 or 1. Right? So in general, if I write it in base k, if I try to represent any integer in base k, then I can write it as summation I equal to 0 to infinity alpha I k to the I, where each alpha I, each of these coefficients is in between 0 and k minus 1. Right? So you're all familiar with this. This is just high school stuff. Right? Now I can also write any number between 0 and 1. Suppose that I have any number r which is between 0 and 1. I can also write this in base k. So I can write r as summation I equal to 0 to infinity alpha I r to the minus I. All right. So if r is strictly less, if we know that r is strictly less than 1, then you can take the summation I going from 1 to infinity, and each alpha I is between 0 and r minus 1. Let's take an example. So suppose I have 0.23, right? I can write 0.23 in base 10. This would just be 2 into 10 to the minus 1 plus 3 into 10 to the minus 2, right? So that is what I write as 0.23, and I'll explicitly write this in within brackets as that this is base 10. Okay, so this is, so when I write 0.23 in base 10, it is 2 into 10 to the minus 1 plus 3 into 10 to the minus 2, right? So if I write 0.23 in base 5, then this notation means that it is a following number. It is 2 into 10 to the 2 into 5 to the minus 1 plus 3 into 5 to the minus 2. So what will this be equal to?
Point 0.52.
Okay, so 0.52. So it is 0.52 in base 10. So 0.23 in base 5 corresponds to 0.52 in base 10. Correct. So it's the same number. If I take a point on the real line between 0 and 1, then the point that I have here would be somewhere just a little past halfway mark. So this would be 0.52. 0.52 to base 10, or it's the same as 0.23 to base 5. Okay, so now suppose I have, let's take 0.23 to base 10. Now I want to find the binary representation of this particular number, right? I want to convert this to base 2. How would you do it?
So like the
Hmm?
conventional method is like for decimal we multiply by
Okay,
2.
multiply by, sorry, can you repeat? I didn't hear the last part.
So we multiply by 2.
Yeah, so you keep multiplying by 2, and then, so suppose I want to find B1, right? So this is B1 into 2 to the minus 1 plus B2 into 2 to the minus 2 plus B3 into 2 to the minus 3, and so on, right? So now if I first want to compute B1, then how would I do it? Right? You would first multiply by 2. What do you get?
0.46.
0.46.
The
So
carry
what would you conclude B1 is?
0.
It is 0, right? So 0. Okay, now how do you find B2?
Uh, Again, this 0.46 into 2, which is
Correct. So
0.92.
0.46 into 2 is 0.92.
Again, 0.
So it's again
2 is
B2 is also 0. Now the third bit,
1.84.
okay, so it's 1.84. So what is the third bit?
1.
It is a 1. And now how will you find the fourth bit?
Uh, 0.84 into 2.
Correct. So 0.84 into 2,
1.68.
1.68. So the fourth bit is a 1. All right, and then again you keep doing the same. Take 0.64 into 2, and you keep going on, right? So 0.23 to base 10 would be 0.00111 and so on in base 2. Correct? And this mapping is unique, right? So if I give you a number in base 2, you can convert it to base 10. If I give you a number in base 10, you can convert it to base 2. So it doesn't matter what k is, you can always convert it to base k. Correct? So this, we'll see that this is important in designing the Shannon-Fano-Elias code. Okay, so any questions so far? Okay, so that's good. Now let's go back to the Shannon-Fano-Elias code. What am I doing? I gave a particular scheme, and the scheme is as follows. Given a particular probability mass function, you compute f bar of x, convert it to binary, and then truncate it to a certain number of bits. Okay, so let's take an example. All right, so example. Let's take 4 symbols. So px is going to be, let's say 0.5, 0.3, 0.1, 0.1. Okay, so this is my px. Now the first step is compute f bar of x. Right, so for each symbol, each of these symbols, so this is 1, 2, 3, and 4. This is my alphabet. Now I want to find f bar of x, which is summation a strictly less than x, p of x, plus p of x divided by 2. So what is f bar of 1? So f bar of 1, well, there are no symbols less than 1. So this would just be p of 1 divided by 2, which is what?
0.25.
0.25. Okay. Now let's see. So this is 0.25. What about f bar of 2? Again, let's use this particular formula. So it is p of 1 plus,
Sir,
yes,
1 minute. The summation, that formula you've written, it is
correct.
px of a plus px of x minus.
Okay, sure. Yeah, thanks for correcting me. Yeah. Okay, so f bar of 2 is px of 1 plus px of 2 by 2. What will this be?
0.65.
0.65. So this is 0.65. And what is f bar of 3?
Px of 1 plus Px of 3 by 2.
No, it's px of 1 plus px of 2 plus px of 3 by 2. Right, so it's the sum, you sum over all symbols less than x,
0.8.
which is in this case is 1, 2, 1 and 2, plus px of 3 by 2. How much did you say it was?
0.85.
0.85.
0.85, okay. 0.85. And now I want f bar of 4.
0.95.
Okay, so this is px of 1 plus px of 2 plus px of 3 plus px of 4 by 2, and you say it is 0.95. Okay, so the first step was to compute f bar of x. Okay, now let's see how many. We now want to convert this to binary, but let us first see how many bits we want to compute in binary. So we have this, we've computed this already. So this is our f bar of x. Now I also want to compute L of x, which is ceil log 1 over p of x plus 1. Okay, so this is going to be my L of x. Remember that p of x was 0 0.5, 0 0.3, 0 0.1, 0 0.1. Correct? So can you compute L of x for all of these? So it's C log 1 over P of x plus 1.
For 0.25 is 3.
No, so you have to compute log 1 over P of x. Not log 1 over f bar of x.
Okay, okay, sorry. Then it's 2.
Okay, so this is 2. Okay,
3.
so Anmol says it's 2355. Is that correct? 2, 3, 5, and 5. Nadine has also confirmed it. So just check. It might be 2, 3, 5, 5. Okay, whatever. So L of x is 2355. So basically we want the first 2 bits in the binary representation of 0.25, the first 3 bits in the binary representation of 0.65, 5 bits in the binary representation of 0.85 and 0.95. So let's try to do that. So we want 0.25, the first 2 bits in the binary representation of 0.25. So 0.25 into 2. Let me maybe write it down separately. I have 0.25 and I want to compute the binary representation of 0.25. So 0.25 into 2 is
0.01. It comes out.
okay. So this is 0.01, correct? Good. So what are the first 2 bits? It's going to be 0 and 1. Okay, so these 2 are what are important to me. Now let's take 0.65. I want the first 3 bits in the binary representation of 0.65 into 2. I keep doing it.
101. 0.101.
0.101 and something, maybe something, it may go on, but the first 3 bits are 1, 0, and 1. Now, what about the next symbol? What is 0.85?
Uh, 110.
We want 5 bits.
11011.
11011. Okay, so the first 5 bits are 11011 and 0.95.
One 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 zero zero.
11100. Okay, something. It would go on, but at least what we're interested in only the first 5 bits. All right, so the code words are going to be the following. So 1 will get mapped to 0, 1, the first 2 bits. The second symbol, for the second symbol, the code word is going to be 101. For the third symbol, the code word is going to be 11011, the first 5 bits in this binary representation.
Sir, for last, I think 4 ones and then 1 0. Sorry.
Okay, 4 ones and then 1 0. Fourth one is going to be 4 ones and then a 0. Okay, so this is going to be the Shannon-Fano-Elias code. Right? So this is the Shannon-Fano-Elias code, and so let's take a step back and think about it. So is this code prefix free?
Yes.
Yeah, it is prefix free. No code word is a prefix of any other code word. So that is good, at least for this example. I'm not made any general statements here. So this is a prefix free code. And let's try to compare it with our Huffman coding or the Shannon coding procedure. In both those cases, we were trying to construct the code word tree. Whereas in this case, we didn't construct any sort of code word tree. The operations were pretty simple. We had a bunch of arithmetic operations, which is basically multiplications and divisions and so on. All right. So ultimately, what did we need to do? We had to compute this f bar of x, right? And then L of x. And maybe what is important to note over here is that suppose that I want the second code word, right? The second code word. Then I can actually construct the second code word without constructing any of the other code words, right? So what would I suppose I know that the symbol is 2, all right? And then what do I need to do? I just need to compute f bar of 2. I need to compute L of 2, all right? And then just write it in the binary representation. So even without computing the other code words, I can compute the code word for this particular symbol, right? And that is going to be the key point in using the that's the key advantage of the Shannon-Fano-Elias code. To find the code word for any one symbol, we do not have to construct the entire code book. Right. So remember that in the in the Huffman coding procedure, well, if you want the code word for one symbol, then you have no way of obtaining it without constructing the entire code word tree. For the Shannon code, even there you have to take the entire code word tree, find all the symbols. You construct it in this greedy fashion, and so indirectly, even if you want to encode a single symbol, you have to find the code words for all of the other symbols. Whereas in this case, it seems to be simpler, because once you compute f bar of x and L of x, that is all that you require, right? And that seems simple, and it's an advantage that we will make use of as we go along. Okay, so just keep this in mind. So this key advantage that we can construct code words on the fly without constructing the entire code book. All right. Any questions so far? Any question regarding the example?
Sir, so we are clearly stating that this is not an optimal code. The three properties which are to be followed for the optimal code are not mentioned.
Sorry, your voice is there's a little bit of disturbance. Can you repeat?
Like the three properties for the optimal code words.
Correct. Even this has the tree property. You can construct a code word tree, but so even for this you can construct the code word tree, right? So it is going to be 0, 1, 0, 1. So 0, 1. This is not an optimal code. Clearly, just by looking at this, you can say that this is not an optimal code. 1, 0, 1. But this is still prefix free, so you can write it as nodes on the sort of code word tree. 0, 1 and 1, 1, 0, 1, 1. It seems like a horrible code. 1, 1, 1, 1, 0, because you're using too many code words. Certainly, you could get rid of many of these bits and still end up with a prefix-free code. So, for example, if you recall in the Shannon code, each symbol was represented using only ceil of log 1 over p of x bits, not ceil of log 1 over p of x plus 1 bits. So you're always one bit worse. So every code word is one bit longer than the Shannon code. But so this is a price to pay, but the advantage you gain is in terms of computational complexity. And for small alphabets, this is not good. It's clearly not a good code construction. But we'll see that when we want to construct code words for sequences of symbols, we can do it on the fly. And in that case, the gains that we will get is going to be huge. Okay, does that answer your question?
Yes, sir.
Yeah. So I repeat, by no means is this an optimal coding process. Is this an optimal code? So certainly the Huffman code will do a lot better than this, and in terms of expected length, even the Shannon code does better than this. But we'll see that this has advantages. So in particular, this is the big advantage that we will leverage in order to construct the codes for sequences. Any questions?
Sir,
Yes.
we are saying we need not construct the entire code book to find the code word of one
Correct.
symbol, but when we are encoding, we are transmitting, and then we are decoding. So we need the code word for all the symbols now, sir. I'm not understanding what is the what do we gain by getting the code word of only one symbol?
Okay, so here, so let's say that beforehand, someone gave you p of x, and someone just gave you p of x. Okay, so right now you have not observed any symbol yet. So let us say that you just pre-compute f bar of x and keep it with you. Only f bar of x. Or let's say that you don't even compute f bar of x. All you know is just p of x. And then now let us say that you have to encode symbol 2. All right. Is this setup clear?
Yes, sir.
Okay. So now I just want to encode 2. Do I need to find out what the code word is for this symbol and this symbol?
No, sir.
No, right? So just all I need to do is just take 0.5 plus 0.3 by 2, compute that. That's going to be 0.65. I need to compute log 1 over p of x, which turns out to be 3. I just need to compute the binary representation of 0.65 up to the first 3 bits, and then I just transmit those 3 bits. Correct? That's going to be my encoding procedure. You're right? Do you agree?
Yes, sir.
Correct. So in doing this, in this entire encoding procedure, I did not have to construct the rest of the code words. I didn't have to compute any of these. I didn't have to compute any of these. Do you agree?
Yes, sir.
Yeah. So now, well, this is a toy example where you have very few symbols. Now, let us suppose that my alphabet consisted of maybe 1,000 symbols. It's a large alphabet, right? So among 1,000 symbols, now if I try to do the Huffman code, then I have to construct the entire code word tree. So basically, and that, remember, that is the only way I can encode, right? Even though I want to encode a single symbol, I have to construct the entire code word tree and obtain the code words for all 1,000 symbols. Whereas in this case, I don't need to find out all the 1,000 code words. I just find out the code word that I am interested in.
Yes, sir.
All right?
So, like beforehand, instead of encoding all of them on the go, you
Exactly. You can do it on the go. You can do it on the fly. Right? So you don't need to pre-compute the entire code book and then choose which code word for the symbol that I have observed. I can observe the symbol, compute that code word on the fly, and then transmit it.
Okay, sir.
Okay, the advantages will become obvious once we get into arithmetic codes. Okay, so we'll see that even for sequences, we'll be able to compute the code words on the fly. Okay, but more about that later.
Sir,
Yes.
how are we sure that we'll be getting prefix tree codes, or for that matter, non-singular codes for this kind of situation?
Exactly. So that is what I'm going to get into next. Right now, we've only seen an example. What we still have to show is that this procedure, the Shannon-Fano-Elias coding procedure, will give me a prefix-free code, or as Varun pointed out, even a non-singular code. Okay. So let us think about this particular coding procedure. Compute f bar of x for all x, and then look at the first L of x log 1 over p of x plus 1 bits of f bar of x. Let us think about this visually. Okay. So you have 1, 2, 3 up to m. So this is x, and let me plot f of x, the CDF of f of x. Okay, so it's going to look something like this. And so on. So all of these are going to be between, so assume that this is whatever, 4, this is 1, this is 0, correct? So here, what is f bar of 1 going to be? Where is it going to lie? So f bar of x is going to lie somewhere along this, right? It is p of 1 by 2. Where will it lie? This is f of 1.
Middle.
Exactly. So f bar of 1 is going to be in the midpoint. What about f bar of 2? Where will it lie? This is f of 2. This is f of 3. Where will f bar of 2 lie?
Midpoint of the
Midpoint of this. Right? So this is going to be f bar of 2. Similarly, f bar of 3 is going to lie on the midpoint of this interval, f bar of 3, and f bar of 4 will lie in the midpoint of this interval. And this is f bar of 1. Okay. So one way to sort of, the intuitive way of thinking about the Shannon-Fano-Elias coding procedure is the following. Now let us look at the CDF f of x. Okay. The whole idea of in Shannon-Fano-Elias coding is to map intervals, disjoint intervals, to individual symbols. So corresponding to each symbol, corresponding to symbol 1, I will identify this particular interval. So I'm looking at the interval from 0 to 1. So I'm looking at this interval from 0 to 1, and I'm partitioning the interval into subintervals. So I have the interval from 0 to 1, and I'm partitioning into subintervals f of 1, f of 2, f of 3, and so on. Okay. Now this is going to be the interval corresponding to symbol 1. This is going to be the interval corresponding to symbol 2. This is going to be the interval corresponding to symbol 3, and so on. Okay, so there is this mapping. Now I haven't come to Shannon-Fano-Elias coding yet, but there is this mapping that I can think of, right? So each of these intervals corresponds to one particular symbol. So the interval corresponding to symbol I is between 1 and m, is basically the interval from f of I minus 1 to f of I, where f is my CDF. Okay, and f bar of I is basically the midpoint of the interval. F bar of I is the midpoint of the interval. Great. All right, so now let us look at one particular symbol. Right, what am I doing in the Shannon-Fano-Elias coding procedure? So for symbol I have this interval f of I minus 1 to f of I. F bar of I lies somewhere over here. Right? It's the midpoint, f bar of I. Now, if I had an infinite, if I represented f bar of I using an infinite number of bits, the complete representation, then it would correspond to exactly this point, the midpoint of the interval. Okay. Now, if I truncate f bar of I to a certain number of bits, so let me, so look at f bar of I truncated. Okay, only the first some L bits of f bar of I. So let me call this. So I'll use this notation f bar of I within square brackets subscript L. So this is f bar of I truncated to L bits. Where will this lie? Will it lie to the left of f bar of I or to the right of f bar of I?
Left, sir.
Exactly. So it's going to lie to the left of f bar of I. So it would be anywhere over here. But But if I truncate it to exactly L bits, then what can you say about, so obviously f bar of I is going to be greater than or equal to f bar of I truncated to L bits, because this would have been summation I equal to 1 to infinity, whatever, let's say f subscript I 2 to the minus I, whereas this is summation I equal to 1 to L f subscript I 2 to the minus I. So I'm removing some of the terms in this in the summation, everything beyond L, and therefore this is going to be less than or equal to f bar of I. Okay, so that is point number one. Now, what is the maximum difference between f bar of I and f bar of I truncated to L bits? How large can it be?
F bar of I itself.
Can it be that bad? So I'm keeping the first L bits, remember? So let's think about this. What is the error going to be? So the error is exactly summation I equal to L plus 1 all the way up to infinity, f subscript I 2 to the minus I. And remember, each fi is either 0 or 1. This is a binary representation. Correct? So it's summation I equal to L plus 1 to infinity, fi 2 to the minus I. So any hints as to how large this can be? So what is the worst that can happen?
2 power minus L double prime.
Sorry, your voice is not audible.
2 power minus L double prime. Like if you can take the first L bit of the maximum and move it out of it, that will be like a geometric sequence converging to some value.
Correct. Sorry, but there's a lot of noise in your audio. But anyway, I think I get your point. So it's summation. So in the worst, what is the worst that can happen? So this is exactly this error. This difference is exactly equal to this. And in the worst case, all the FIs could be 1. So the FIs are either 0 or 1. And the maximum value that this can take is when all the FIs are equal to 1. So it is summation I equal to L plus 1 to infinity. Fi is 1 into 2 to the minus I. Now, what is this equal to? What is this geometric series going to be equal to?
2 to the power minus L.
2 to the power minus L. Correct? So in the worst case, this difference is 2 to the power of minus L. So now let us go back to this picture that we had. Now this is f bar of I, right? So in the worst case, f bar of I is within some interval. So this the code word. So f bar of I truncated to L bits is going to lie somewhere in this interval of length 2 to the power minus L. Correct. So f bar of I is going to lie somewhere in this green interval. And the length of this interval is 2 to the power minus L. Is that clear? So 0 to 1. I'm partitioning this into intervals. This is, let us say, f of 1, f of 2, f of 3, and whatever f 4, which is equal to 1. This is f bar of 1, this is f bar of 2, this is f bar of 3, this is f bar of 4. Now, what are the code words? The code words are f bar of I truncated to L of x bits, correct? So they're going to lie somewhere to the left. It's going to be some point to the left of this, and the maximum difference between that point, between the code word and f bar of x, is at most 2 to the minus L of x. So f bar of x minus f bar of x truncated to L of x. Remember, this is the actual code word. So this quantity is less than or equal to 2 to the minus L of x. Correct? But what is L of x? This is 2 to the minus ceil log 1 over p of x plus 1, which is less than or equal to 2 to the minus log 1 over p of x plus 1, which is what? It is just p of x divided by 2. Do you agree? Any questions so far? Right. So what am I doing? So what I'm doing now is basically it's a different representation of the code word. Right. So the code word is a sequence of bits, but then right now I'm thinking of this sequence of bits as a real number. Right. Remember, the way I'm obtaining the code word is I'm computing f bar of I. I'm truncating it to L of x bits in the binary representation. And that is going to be my code word. Now I can think of my code word as a sequence of bits, but then I can also think of this as a real number. All right. So f bar of x truncated to L of x bits. This is some real number. So it's a sequence of bits 0.1011, or this is of course, in binary. Or I can treat this as a real number. I can look at the decimal representation of this. So it is 2 to the minus 1 plus 2 to the minus 3 plus 2 to the minus 4 plus 2 to the minus 5. So it is some real number, and I'm representing that as a point on this interval 0 to 1. Okay. And now what I've just shown is that f bar of x minus f bar of x truncated to L of x is at most p of x by 2. So it is going to be less than f bar of x, but how far can it be from f bar of x? At most p of x by 2. But what is this width? This is p of x by 2. Right? So what this means is that the code word is going to be some point. The Shannon-Fano-Elias code word is going to be some point on this interval. All right, so the code word for 1 is going to be somewhere in this interval. The code word for 2 is going to lie somewhere in this interval. The code word for 3 is going to lie somewhere in this interval. The code word for 4 is going to lie somewhere in this interval. Okay, it's going to be somewhere along this interval. So it is some real number. Okay, so now since these intervals are disjoint, it is going to be some point. Maybe this is the code word here, this is the code word for 3, this is the code word for 4, and maybe this is the code word at this point for 4. So what can you conclude based on this? What property can you conclude? Can you say that this is going to be a non-singular code? Yeah, so it is going to be non-singular, right? So take any, so what do I need to show? So take any two symbols, x and x prime, x not equal to x prime. The code words are basically represented as f bar of x truncated to L of x and f bar of x, x prime truncated to L of x prime. So these are whatever, you can think of this as a sequence of bits, but you can also think of them as two real numbers. Now, can these two real numbers be equal to each other?
No.
No, sir.
They cannot, right? Because they're going to lie in disjoint intervals. So f bar of x, maybe if x is equal to 4, f bar of 4 is going to lie somewhere in this f bar of 4 truncated, the code word is going to lie somewhere in this interval, whereas for 3 it is going to lie somewhere in this interval. The intervals are disjoint, so the intervals on which they can lie are disjoint. So these two are never going to be equal to each other. So therefore, these two are non-singular. Okay, good. All right, I'll just take 2 more minutes. So now we also need to show that this coding scheme is prefix free, right? So now let us think about a particular sequence. So let us look at f bar of some f bar of 2. Okay, so let's look at one code word. So it's going to lie in this interval. Let us say this is f bar of whatever x truncated to L bits. Right? So this is the code word corresponding to symbol x. What can you say about the set of all suffixes? So this is going to be whatever 0 point in binary 1011, right, and so on. So you have truncated it to a certain number of bits, right? So now you want to make sure that no other code word is a okay. So what I want to show is that this is not a prefix of any other code word. Okay, we want to show that the code word for x is not a prefix of any other code word. Now, if I look at all the code words, all the numbers which can be, for which this can be a prefix, what is it? It should be some sequence of bits following this, right? It could be all zeros, 0, 0, 0, 0, 1, 1, 0, 0, and so on. So everything following this is a valid sequence for which this is a prefix. So the set of all sequences for which this is a prefix. So there is some interval which contains all the sequences for which this code word is a prefix. So all of these sequences are going to lie to the right of this particular point, to the right of this particular code word, right? And what is the length of this interval going to be? So this is L of x bits, and basically everything following this is going to be a prefix. Sorry, is going to be a sequence for which this is a prefix. Correct? So my claim is that this interval, let me call this S, the size of this interval, S is 2 to the minus L of x. Right? So in the worst case, so this could be all zeros, but in the worst case, this is all ones. Right? So the length of this particular interval is summation I equal to L plus 1 to infinity, again 2 to the minus I, exactly the same calculation that we had, and this is 2 to the minus L. Right? So the set of all sequences for which this code word is a prefix is going to lie within an interval of size 2 to the minus L of x. Now let's go back to this picture over here. Let me copy this. So my code word lies somewhere over here. This is the code word. It's going to lie somewhere on this interval, and all the bad sequences, that is the sequences for which this can be a prefix, is going to lie within another interval, and the width of this interval is 2 to the minus L of x. Correct? But what is 2 to the minus L of x? This is P of x by 2. So for every symbol x, so you take any symbol x, you have, so for every symbol x, I have f bar of x. The true code word is going to lie somewhere on this interval. This is going to be the true code word. And the set of all bad sequences, that is a set of all sequences for which this could be a prefix, is going to lie in another interval. But the length of this interval is P of x by 2. So the code word is going to lie within this interval of length P of x by 2. And all the bad sequences are in this interval of length P of x by 2. But no matter what happens, all of these, both the true code word and the set of all bad sequences, all of these are strictly going to lie strictly within this interval, which is f of x minus 1 to f of x. Okay, so they never overlap, and therefore no other code word can be a prefix of this particular code word. All right. So I'm already over time, so let's stop over here.
Sir,
Yes.
just can you repeat? These two will not overlap, you're saying?
Oh yeah. So take the sequence. Okay. Let me perhaps just repeat. So what is going to happen? So take any particular symbol. Let us look at x. F bar of x. This is f of x minus 1. This is f of x. And whatever, this is f of x plus 1. Now the true code word is going to be some point. It is going to lie somewhere over here. It is going to lie within this interval. That is what we are guaranteed. So the blue point, which is the true code word, f bar of x truncated to L of x bits, is going to lie within this interval. It's going to lie to the left of f bar of x, but strictly between f of x minus 1 and f bar of x. Now, what about all the sequences for which the code word is a prefix? All these sequences are going to lie within this interval, and the length of this interval is p of x by 2. All right. So these are all the bad sequences. So we want to make sure that no other code word lies in this particular interval. Right. So this is the interval of sequences for which this code word is a prefix. Okay, but what we know about this, since this is p of x over 2 and this is always to the left of f bar of x, this bad interval is going to be strictly less than, it's going to be within f of x minus 1 and f of x. That is guaranteed, because this distance is p of x over 2 and this can only be to the left. So both the bad interval and the true code word is going to lie within this interval. Both the code word for x and bad sequences are going to lie within the green interval, and that is f of x minus 1 to f of x. But now, what about the code words for other symbols? None of them are going to lie within this particular interval. That we've already seen. We know that all the code words are going to lie. So the code word for x plus 1 is going to lie in this region, in the yellow region, somewhere over here. So this code word can never have this code word as a prefix.
Yes, sir. Got it. Thank you.
Okay, fine. Yeah, so just go through the proof once again. It's there in the Cover and Thomas textbook. And anyway, there's also the recording. So it might take a little bit of time to grasp it, but it's nothing very complicated. It is just you think about code words and the set of and the set of bad sequences as intervals, and you just make a notice that these can never overlap with each other, and therefore the code is non-singular and it is also prefix free. All right. So let's stop at this point. We'll continue in the next class. Any questions? Okay, so see you all in the next class.